Hey there everyone, welcome back. So this will be version 2 of the problem with the mass on the horizontal beam, right? We left off on this slide and we found the torque from the leftmost point, right? I called that really L equals 0 because again this beam is of total length L. So we calculated this torque expression from the left point. In this video, I'm going to calculate the torque and really get these exact same final answers for FR and FL, but from different locations along the beam, and show you that it still works. So I've copy pasted that free body diagram. I've added some distances here, right? The block, its weight is acted at L over 4 from the leftmost edge, and the beam, because it's of uniform mass distribution, right? It's even constant density. Its weight is acted at the center. In other words, L over 2 from the edge. Okay, so now let's do the torque. Let's calculate the torque from the rightmost edge. Okay, see what we get. So sigma tau, actually let me do this from FR, okay? See what we get, sigma tau. All right, so now keep in mind that torque is R cross F, right? It so happens that in this problem, all of the forces will be perpendicular to R, okay? And that's kind of on purpose in this case. In other words, the beam is always horizontal and the forces are always vertical, okay? From the right point right here, let's see, positive torque is coming from any force that would rotate this beam counterclockwise, right? So those two gravitational forces. So that means our first one will be positive. Let's do the beam itself. So positive L over 2, that's R right here. That's the R, the vector, the magnitude of R in this case, times the force, which is of magnitude mg. Sine 90, of course, is 1. And we're adding the second torque from the block. So that's at a distance from the right point of, that's L over 2 plus a quarter. That's a total of 3L over 4 times the force of capital Mg, okay? And we're subtracting now the torque due to the left scale, right? That's preventing a rotation in the counterclockwise direction, which really effectively means it would rotate it clockwise. Again, these are all hypothetical. The magnitude of that R vector is now the entire length of the beam, right? FL is acting at a distance of L from our axis of rotation over here. So L times FL, and that equals 0, okay? And now, like before, our ultimate goal is to solve for the magnitudes of the two forces from the scales, FL and FR. So actually, like before, we can solve straight away the torque equation for FL in this case. So if I do that, notice that the actual magnitude of L can be canceled out. And then we just have basically 1/2 mg plus 3/4 capital Mg minus FL, right? And I'm going to take, whoops, sorry, equals 0. If we take FL to the other side, that really just kind of, takes that away and turns it into this. And if we plug in those numbers, I might as well show you here. The mass, little m, was 1.8. Capital M was 2.7. We get the same value. So FL is the 28.7 newtons, right? And if we go back, FL was again 28.7. But notice, right, it's a slightly different equation, right? Even it's slightly different from FR, right? So if you choose a different axis location, the equations won't necessarily be the same. In fact, most times they won't, okay? So that's the torque as from the very rightmost position. Let's do it again, but from the center, okay? The center. Again, this is hypothetical. The beam won't actually rotate about the middle, right? It just won't, right? That gravitational force is an external force. There's really no physical point here that it could rotate around. In actuality, this beam does not rotate. But again, it's theoretical, hypothetical, whatever word you want to use, and that allows us to pick any point for our axis that we want. Okay? So now, let's kind of draw a line and do it again. So from, I'll say the very center, the center of mass. Okay? So the very center right there. Sigma tau, again, which forces will give us a positive torque? Which forces will cause a counterclockwise rotation around that point? Well, the weight of the block, right? That would cause it to fall down. So that's positive. The magnitude of that R is that distance, right, which is L over 4. And the force is capital mg. Let's see. The other positive torque would come from FR, right? That force would cause it to, rotate that direction, counterclockwise, or up about that point. And so this R vector right there is L over 2. Right, and now we have the force of FR, okay? And our negative torque comes from FL, right? It's very similar to the term we just wrote, but it would rotate it clockwise. So we have negative L over 2 FL, and this equals 0, okay? In this case, because we chose an axis that was not at the location where one of our unknowns was being acted, that means those unknowns are in that equation, here and here. So we cannot straight away solve for FR or FL. We have to now use the force equation, okay? And so now we have two equations and two unknowns. So I'm going to solve the y equation, right, this one. I'm going to solve it for FL. And then I'm going to plug that expression into FL in the torque equation, then solve for FR. Okay, so that's my strategy here. So first, FL equals positive mg plus lowercase mg minus FR. Right? Again, that came from solving this equation for FL. Now I can plug this expression, right, all that into the torque equation. Right? Do you see what else we can do? Like before, the magnitude of the length of the beam, L, cancels out again, which is really handy. And so we basically have 1 over 4 mg plus 1 over 2 FR minus 1 over 2. Now plugging in all of that circled stuff. So plus the two weights minus FR. And all of that equals 0. I'll put the 0 on the left side to save space. Okay, now we just have one unknown, FR and FR. So Let's distribute the 1/2, combine like terms, and solve for FR. So we have 1/4 mg plus 1/2, whoops, it should be FR, not RF, minus 1/2 capital MG minus 1/2 lowercase mg, and then plus 1/2 FR, right? This is just straight math part, right? So almost there. We're getting there. Solving for FR, I can combine this 1/2 F and that 1/2 F to give, well, 1, right? And so I'm going to combine those two terms and then take every other term. So this one, and this one. I'm going to take all those to the other side. Okay? And I'm doing that to get the following expression. Now let's see. That becomes positive 1/2 capital MG plus 1/2 lowercase mg, and then minus 1/4 capital MG. Okay, combining like terms again, right? We have capital MG, so a positive 1/2 minus a 1/4 gives us, what is that? Plus 1/4 mg plus 1/2 lowercase mg, and this is our expression for FR that we should have gotten in the first video, right? So if we solve for this, plug in the values FR, we should again get the 15.5 or 15.45, whatever, right? Newtons. So let's scroll back and see if that's the same expression. It turns out it is, right there. 1/4 times capital MG plus 1/2 lowercase mg. It's the same expression here, but I think you can see that it's a much more complicated way of getting that. Okay? And so this just goes to show you that if you choose, an axis location here, what you're trying to solve for are actually the forces there and there. So those won't cancel out in your torque term. So I suggest when doing these problems, choose, say, if you're solving for two unknowns, choose the location of one of those unknowns, okay, to make your life a little bit easier. If you would like to, do this again, right? Calculate the torque equation and the final answers for an axis of rotation 3/4 of the way from the left position. See if you get the same thing. All right? With that, thanks for watching.